Hello and welcome everyone to the 12th lecture of our CUDA programming. So in the previous lecture, we saw bank conflict in detail, right? So we saw what is bank conflict and what are the issues with it, and how is it associated with the shared memory and so on. And then we also looked into the examples related to no bank conflict, the code snippets related to no bank conflict, and the code snippet corresponding to the bank conflict case. Then we visually saw the different examples for the case of no bank conflict and for the case of bank conflicts, right? So we visually saw the examples, and then we briefly touched upon the textured memory and its example on how to use the textured memory. Then we also saw the use case for the constant memory, right? So we saw how to use the constant memory with an example. And then we saw that what is CUDA compute capability, and then we saw like there is some major number and minor number associated with it, and we saw that how that compute capability is associated with the features that are associated with that family of GPUs. And we saw that typically higher the major number, more the feature it supports compared to its predecessors. So we saw all those things, and towards the end of the previous lecture, we concluded the memory aspects of the GPU. So that is where we ended for the previous lecture, and so with that we completed the memory aspects. So that was the outline for the previous lecture. For today's lecture, we are planning to cover the synchronization aspects, at least few of the synchronization aspects. So for today's lecture, we'll be covering, first of all, we'll seeing what is data race. We'll understand it in detail. We know in high level what is data race, right? We saw in the few of the lectures of memory what is data race. But we'll cover this data race uh, in more detail here in the synchronization part. Then we'll also see different examples related to the data race. We'll also see the essential conditions needed for data race to happen, and we'll also see we'll also see some ways in which you can mitigate the data race. Then we'll see multiple examples related to the data race. Yeah, and then after seeing those multiple examples for data race, we'll today see a small, we'll see a use case for two threads which are executing in parallel, and let us say for those two threads we want to implement some sort of synchronization between those two threads. Then how can we do that? So we'll be looking that in the today's lecture. So that's a brief kind of outline for the today's lecture, what we want to cover today. That's our agenda for today. So with this, let's get started for the today's lecture, which is our lecture number 12. Okay, so coming to synchronization, first of all, let us start with its definition. What is synchronization? So from parallel programming perspective, what is synchronization? So when we have multiple threads working to achieve some particular task, what is synchronization? Synchronization is nothing but the coordination among the threads to achieve the particular task. So when there are multiple threads, it might happen that our computation is such that we want our threads to coordinate with each other, so that the task that we want to accomplish can be done without any data races. So that is what it is, and we'll see particular examples related to it. But that's the brief definition about it. Okay, so coming to the case when there is no data, coming to the case where there is no synchronization needed. So quickly I'll give you that example which I used to give every time, that classic example, right? That we want to initialize array with all zeros on the GPU. So if you remember that, for that we need to just launch a kernel, pass that array uh, array inside that kernel, pointed to that array which points to some GPU memory location inside that kernel, and we then each thread compute its ID, and then we do that ARR of ID equals to 0. So that is a very nicely parallel operation, or embarrassingly parallel operation, where we don't need any synchronization, right? Threads can perform their own computation independently. They don't need to coordinate with each other or talk with each other in some sense to achieve that task. So that is a very hypothetical scenario. Yeah, I mean, that is quite useful, but you might see, I mean, we in today's lecture will see the multiple scenarios where threads will need to coordinate with each other. But yeah, for just for the sake of starting, that was the example where we don't need any synchronization. So that's one case. Second case is where we need synchronization, and that will be looking in today's lecture. Multiple examples for it. Yeah, so that's one point. And the another point related to synchronization that I want to make before starting is that yeah, so the cost incurred for this synchronization is very, very high if you see, like uh, as compared to memory and computation. So typically computation takes very less time because let's say you want to do some 1 unit of operation, then each thread as it is assigned to the GPU core can do that operation in one cycle, one GPU cycle, right? So typically one GPU cycle is very less time. So computation is really very fast. Then comes the access to the memory. For memory, there are two cases, right? One is shared, I mean, not two cases, multiple cases, like whether it's a register or shared memory or the DRAM of the GPU. Based on which scenario it is, it might take multiple cycles. For accessing registers, it might take some 2 or 5 cycles. But for accessing shared memory, it might take 20 or 30 cycles. And for global memory, it might take 400 or 800 cycles, right? So computation is fastest. Then comes the memory, which is slower than the computation aspect. And if you see, the synchronization is even more costlier than this memory aspect. So okay, so point that I'm trying to derive here is that let's say your code that you have written is having everything. It has I mean everything in the sense you are using synchronization among threads. You are also having uncoalesced access. You are also using shared memory where there are bank conflicts, and obviously there must be a computation. Otherwise, why will you use GPUs? So if that is the case, you have everything, then first what you should try is to reduce, I mean, remove this, I mean, not remove, but try to write your code in such a way that you can do same task without synchronization. Or if it is possible, you should try to do that. After that, you should try for coalescing the memory access, then band conflict, and then some computation aspects like thread divergence and all those things you should look at. So yeah, so that is what I want to make, I mean the point that I want to make before starting. So with this, let's get started. Okay, so our agenda for next 5 lectures is going to be this. If you see, we'll be learning these things in next 5 lectures, which is everything about synchronization. So we'll be learning what is data race, what is mutual exclusion and deadlock. If you remember, we have already studied a bit about data race in that shared memory example that we saw in the memory, right? That two of threads were executing simultaneously, and we said that there is something like data race, but we'll see understand here in detail. Then we also have seen deadlock in one of the computation lecture, but yeah, we'll understand it in detail here. And then we'll see what is this mutual exclusion. We'll formally define it, and we'll learn more about it. And then comes 3 important points about this, or 3 important ways in which we can implement the synchronization, or we can implement the coordination among the multiple threads, multiple GPU threads, which is using either atomics or locks or barriers. So yeah, okay, one point here. We have already seen one type of barrier, if you people remember in the memory lecture. Does anyone remember what was that barrier? It was among the
Global value.
no, no. In memory lecture, we saw one type of barrier, if you remember, which is used for synchronizing the threads of the thread blocks. Yeah, threads of the thread block. Quickly, anyone want to point that out? Which was that?
Global barrier.
Global barrier we saw, but like
Sync thread.
yeah, sync thread actually, because sync thread is the one which is, I mean, global barrier is just what I can say. It's not any function. I mean, it's just a uh, I mean, it's just a mnemonic that I used. It's not actually implemented in the CUDA. I mean, it's not, I mean, you won't be able to use global barrier as like writing that global barrier and you'll get the global barrier across all the GPU threads. There is something else to it. We'll learn that also. But yeah, the sync thread, which we learned in the memory that in previous lecture, is used for synchronizing the threads of the thread block. And yeah, so that is one sort of barrier, but it's just a barrier across the threads of the thread block. Yeah, so that is the example of barrier. We'll see what is locks and atomics as we go along with the next 5 lectures. Then we are going to learn these two new things, which is reduction and prefix sum. These two new things we'll be learning, and these are the way. I mean, these are the way in which we compute. I mean, compute the data, and it allows to compute the data. I mean, compute the operation in race-free manner, data race-free manner. We'll learn about these two things in the later lectures. Yeah, so this is going to be our agenda for next 5 lectures, and for today's lecture we will be seeing data race and some bit of mutual exclusion between two threads. Just between two threads we'll be looking this two part. Yeah, so with this let's get started, and for today's lecture we'll be starting with a classwork directly. So yeah, so let's start with the classwork. So I want each and every one of you to write the CUDA code for the to implement the following functionality. So let us say that we have some user-defined data type using struct, which is named as point, and it has two attributes x and y, and then we are declaring array of that type point, which has n elements inside. And what each thread does is it works on 4 elements. So let's say thread 0 takes ARR of 0, 1, 2, and 3. It takes 4 elements, first 4 elements. In similar manner, thread 1 will take ARR of 4, 5, 6, and 7. In same manner, it will go on. So each thread, it takes 4 elements, and it finds the average of x values. So these are the average of x values. And yeah, after finding the average of x values, what it does is it sees the y value. I mean, it checks the y value of all those all those 4 values. And if it sees the y value above the average, any of the y value above the average, then it replaces all the y values, all the 4 y values with average. That is the case one. When it sees any of the y value above the average, it replaces all 4 y values by the average. Otherwise, what it does is it adds y to some global sum, and that global sum, I mean, the variable in which it adds that y value is defined globally for the GPU kernel. Think of it like that. And yeah, so it does that. And on host, what we do is we will print the number of elements set to average here, that we set to average. So this is the functionality that we want to achieve. So I request each and every one of you to try writing the code, or at least some steps corresponding to it, and point out some issues related to this code, like what can be the potential issues that we can face while writing this code. I'll pause here for a few seconds so that you people can try. Just let me go to the chat quickly. Yeah, sync threads is the correct synchronization construct. So specifically, this is the one that we saw in the memory lecture. Yeah, so again, I'll be going back to this. Request each and every one of you to try out this so that we can derive some important point out of this class. Yeah. I'll wait here for a few seconds. There are no responses, so I'll wait for a few more seconds.
Sir, if any y value is above average, you have to replace all of it. Huh?
Yeah, sorry. What are you? Can you reiterate? Sorry.
If any of the four y values are above average, you have to replace all of them with the average, right?
Yes. Yes. If any of the y value is above the average, you need to replace all four y values with the average. You can either write some steps or, uh, I mean, just a brief overview of your approach that you are trying to make to this classwork. Actually, there is some point that I want to derive out of it quickly.
Sir,
Yeah, please.
uh, we can like first release like n by 4 threads of a D kernel in which we can access the elements of number I plus 1, I plus 2, I plus 3, thread IDX, where I is thread IDX dot x, and like for every thread we'll like assign four unique elements of that array,
Hmm.
and then we can calculate the x and replace do those things.
Yes, that is correct. So whatever I don't know, but I think okay. Anyways, so your suggestion is correct. So what we can do is we can so let me build up on that suggestion itself. So what we can do is we can launch a kernel with n by 4 threads, and each thread is working on 4 elements based on its thread ID. So thread 0 will be working on 0 1 2 3 4. Sorry, 0 1 2 3. Thread 1 will be starting from 1 into 4, so it will work on 4 5 6 7. Thread 2 will be starting from 2 into 4, which is 8 9 10 and 11, and so on. That is fine, so that we can do based on the its id. It will be assigned some values. It will find the average values of x. That is also fine because that is local, right? So yeah, so I'm hoping that you are getting it. So each thread can get that local sum and then compute the average of those four values, because no other threads are interfering with those four values. If you are getting it properly, if you see this ARR of 0 to ARR of 3, ARR of 4 to ARR of 7, and ARR of 8 to ARR of 11, all these are independent values, right? So thread 0 will be working on this, thread 1 will be working on this, thread 2 will be working on this. That is okay. But what is next? See, that is fine. They can also compute average without any problem, because each and every thread is working on that four set of elements. But issue comes at these 2 points. Let us understood what this does. So if a thread value sees y value above the average, it replaces all four values with the average. So that is also okay, right? If you see here, let's say this second thread or thread with ID 1 saw that any of the y value here was above the average, then it can replace all the four y values with the average, because again these four values are worked by only thread with ID 1, and no other threads are looking at these four values. So that is also fine. They can replace, so each thread can replace the value of 5. If the value is above the average, yeah, so it can replace all four y values with the average if this is the case. But if it is not, if it doesn't see any of the y value above the average, then what it has to do? It adds the value of y to the global sum. So here comes the problem. So this first of all, this globe, it's the variable in which we are adding the values, it's global first of all. So what will happen? Let us understand this. What will happen? So each and every thread is trying to add some value into global sum based on its thread id. Okay, there is some value which each and every thread is trying to add into this sum variable. And again, so if each and every thread is trying to do this here, if each and every thread tries to add value inside a into a global variable simultaneously, then what can happen? We have seen this, right? The data race can occur here. So more precisely, if you people remember, probably in one of the memory lecture I told that this sum equals to sum plus some value x that we want to. It's broken into 3 statements, right? It's like reading into register first, then register equals to register plus x will happen, and then some will be written back. So it's this statement, just this single statement is composed of these 3 statements. And let us say that 2 threads simultaneously tries to add the value inside this sum variable, which is precisely what we are doing here, right? It adds the value of y into the global sum. If 2 threads or 2 or more threads try to do this sum equals to sum plus 1, what will happen? So let us say both the threads read the value simultaneously. So let us say some value of sum was initially 4. Both the thread would have read the value of sum as 4 into their register. Let's say thread 1 wants to do plus 2 and thread 2 wants to do plus 3. So final result would be 4 plus 2 plus 3, sorry, 4 plus 3 plus 2, which should be 9, right? This is what we expect. When we do 4 plus 3 plus 2, we want the answer to be 9. But since they are executing parallelly, both of them would read the value of sum as 4 into their register. They'll do register plus register equals to register plus x. So thread 1 will be doing 4 plus 2, thread 2 will be doing 4 plus 3. So they have value as 6 and 7 simultaneously into their registers. And then based on which thread is writing last, the value of sum might be either 6 or 7, which is neither of which is correct, right? We want final value as 9. So this is the, if you see correctly, this is the example of, this is the case where the data race can happen. So this is one point where the data race will happen. Can anyone tell me another point where there can be data race in the same when you implement this thing? So this was one of the point where there can be data race. Is there any another point where the data race can happen?
We have to print it. So all of the threads will be trying to print to the std out at the same time.
That is okay. Printing, if you remember, I told that printing will be, the data will be dumped into the buffer and arbitrary order of printing will happen. That is fine. It won't affect the correctness. Printing is like, it's for the sake of user that we want to see the final result, but it won't change the answer or it won't affect the correctness. Here the correctness is being affected. Answer is 9, but it is telling us 6 or 7. That is the problem. In same way, there is some another problem also with this code. Can anyone point out? This was one of the problem due to the data race. There is one more problem with this.
Array of structures.
If you people know this arrays of structures and structures of array, all these are for the optimization purpose. They doesn't affect the correctness. Even if you use structure of array on the GPU, sorry, arrays of structure on the GPU, it will give you correct answer. Just that performance will be lesser, because AOS is better for CPU and SO is better for the GPU, if I'm not correct. Sorry, if I'm not wrong. Yeah, I think yeah, that was the way it was. Anyways, so that won't affect the correctness. It will affect the performance. Is what I'm trying to say. There is one more issue. I'll give you the hint here. It's also related to the data race only. In the same way we are having the in same way we are having some issue here, like while adding. It's the same kind of issue. That is the hint. Okay. Quickly, if anyone is able to point out. Okay, I don't think that this will be issue. It's one because see, replacing the value of 5 with the average could cause conflict. It could cause conflict if, okay, let us come to this point. It could cause conflict if the thread is replacing entire array, entire array with those y values. But here the y values are being replaced for only this 4, let me go back, for only these 4 elements on which it is operating. And if it is replacing on in this only this 4 elements, there is no data race, right? It is the four elements which, I mean, if these are these four elements for which this thread was assigned, right? So that is not an issue. Any other thread won't be ever looking into this I mean, this four values, and so I don't think that that is the issue. It's one. I hope you are getting it. Okay. Anyways, let us continue. I think yeah, but that's good that you have tried. So let us continue. So the second issue is here. The host want to print the number of elements set to average. So printing is not the issue, but it wants to print the number of elements that are set to average. So for counting that number of elements that are set to average here, if you see, it need to count the each and every thread needs to count that how many elements are set to average here, if you see properly, and this will be done inside GPU. So again, each and every thread will be doing something like this count plus plus whenever it is replacing that particular y element by average. This will also cause the data race, right? Because it is like this, count equals to count plus 1. And if you observe properly, entire, I mean, this again statement will be replaced by this 3 statement. And since there can be multiple threads which are sorry, since there are multiple threads which can have this y values above the average, and since they'll be counting all those y values simultaneously, it can happen that again data race can happen while incrementing the count. So this is the second I mean, this is the second place where there can be the issue. This is the first place. So basically, if you try to write the code corresponding to it without atomics or something, like without synchronization, any synchronization construct, then it will be racy, and I mean, there are some chances, or I will say there are chances that it will give you incorrect result because of the race happening here, data race happening here and here. Okay, so any questions up till this point? Uh, on this slide or any of the previous two slides?
Yeah, question on how we will be essentially uh, as achieving the synchronization. Can we do that using global barrier here, or is
Okay,
that a
for
too?
okay, we'll come to this point later. But okay, since you have asked this question, let us pick this question up. Here, there is no need of global barrier as such, because we are just if you see, for both the place that where there is data is happening, where there are data is happening. So in both the case, we are incrementing or adding some value. Then in that case, we can use some atomic instruction, basically atomic add, and we can do this thing. We'll pass the variable in which we want to add the value atomically,
Okay.
and then we can do this, right? Uh,
Understood. So one more question. So either we can replace value, we can give value this particular count or the global value to the function, GPU function, and you can keep on updating that value within, like each thread will keep on updating that value.
yeah.
Other
So
way is we do it in shared memory and return the value and sum the values up uh,
yeah. So
outside.
for okay, so for the second way, I'll tell that if you are only launching the kernel with one block, then it's okay. Otherwise, if you are launching kernel with multiple blocks,
Right.
then
So
you
in
are,
that
let's
case,
say,
hmm,
yeah.
in that case, we have to sum the values for all the blocks for each of these items.
Yeah. Again,
So
that will require
hmm,
some. Yeah, please go
can
ahead.
it be achieved? Can we get the shared memory per block, shared memory value per block for the kernel as an output?
Okay, so you can get that value. I mean, essentially, you can essentially the shared memory is per thread block, right? So essentially, what you can do is you can print the values that are for each. I mean, that are for threads of each thread block. That is okay. That you can do. But the later thing that you asked was unclear to me. What you want to do later?
Uh, since eventually we want to sum up all the values across all the blocks, generally it seems like because even the average value, how many times average has occurred. If you count per each of the blocks and add them up, then it will give you the final answer. So if we can essentially get the value out of each block, and that's the output of the kernel, and you sum them up,
Okay. Yeah.
or
So yeah.
yeah,
Yeah. Please go. What or what?
or combine them in some necessary way, if it's not a sum, or if it's possible to combine them in some necessary way, is it possible to achieve? That's the question.
Okay. So I think it is possible. So let us say that each thread block computed their, uh, computed their sum independently. Each thread of the thread block computed their sum independently. Now let's say we want to combine those values. For that again will need some synchronization construct. Either it should be sync thread. Okay, sync thread will not work because it's only per thread. Threads of the thread block. But again, you will need some atomics, right? Or barrier, some sort of barrier, because again, since what you'll be doing, you'll be choosing representatives out of each thread block, right, to add that the value that is computed by that entire thread block into some global variable. Each representative of that particular thread block will be adding that value inside that global variable. So yeah, so for that again there will be some synchronization needed also. I hope that is clear.
Yeah, that makes sense. Yes. Yeah.
Yeah, so there is, sort of this synchronization is inevitable if there are multiple threads performing this some sort of this operation, addition or subtraction or something like that. Yeah, but we'll see how to reduce the cost for it probably in the next 5 lectures. So yeah, with this, let us move on. So I hope you are getting it that why there is the data is with this, the code that you will implement corresponding to this class word. And we'll see in the coming lectures how to mitigate this issue. So, okay, let's now, as we have seen the example corresponding to this data is, let's now formally see when the data risk can occur. We know what is data risk, right? When multiple threads try to perform the operation on the common memory at the same time, that is the data risk that will get the data risk is what we saw in this previous example. But what are the necessary conditions for the data risk to occur? Let us see that. Let us see those conditions. So for data risk to occur, all of these four conditions should hold. So first of all, there should be multiple threads for the data race to occur. If there is just one thread or single thread execution, then there can't be data race. Yeah, so I hope that is clear. We need multiple threads. Then this multiple threads should be updating some common memory location. So if you see in our previous example, the common memory location that they were updating were this variable count or this variable sum. So okay, let me switch. Okay, so they should have some common memory location, uh, like sum or count that we saw in the previous example. Uh, so there were multiple threads. There was common memory location which was sum or count. Then at least one thread should write. So in that case also multiple threads were writing, right? If you see both the threads or multiple threads were trying to write into that sum or count variable. After reading their value, adding the appropriate content to it, and then every thread was trying to write into it. So at least one write was there. And then there was this concurrent execution also happening, right? That they were trying to write at the same time, or in some interleaved fashion, but they were trying to write concurrently. So yeah, so concurrent execution is also needed. So without concurrent execution, even that, let's say you have multiple threads, but you are executing that piece of code or that addition operation in time, in some interleaved fashion, that let's say first thread is performing, and then only that second thread is trying to add, and then only that third is trying to add the value into it. In that case, there won't be a data risk, but this concurrent execution is important. So without concurrent execution, also the data race is not possible. So all these four things are necessary for the data race to occur. So even if you remove one of it out of this 4 this 4 conditions, if you remove any one of it, then also the data race will, it will not occur. So all these 4 are necessary conditions for the data race. So okay, so we understood that these 4 are the necessary conditions for the data race to occur. So in order to remove the data race, what we can do, since all of these 4 are necessary, what we can do is we can just try to remove one of it, the necessary condition out of it. Then if we achieve that, then we can remove the data race. So uh, that fetches us, uh, takes us to the ways to remove the data race. So these are the 4 ways to remove the data race, and even there can be more ways, but these are 4 ways corresponding to these 4 necessary conditions for the data race to occur. So since since we need multiple threads for data race to occur, this is a necessary condition. Just in order to avoid data race, what we do is just we execute sequentially, just with one thread. So that is one of the way to remove the data race. Then second way is privatization or data replication. So we have this data race because of this common memory location, threads updating in this common memory location, right? So this is causing the issue. This is one of the necessary conditions for data race. So instead what we do is we do thread privatization. That is, each thread has its own local copy of the variable in which it is updating the value. So if that is the case, if there is a thread privatization or data replication among the threads, then again we can avoid the data race, since they are updating in their private copies. So yeah, so that is the way. The third way is separate read and write by a barrier. So this is for the third necessary condition. So at least one write should be there. So what we can do is we can separate read and write by the barrier. So what we can do is we can do all the reads first. So reads can be done parallelly, right? Reads won't cause data race because let us say 100 threads are reading the content simultaneously. There is no race there. But if they try to write parallelly, then the output can be any. I mean, it depends upon which thread is writing the last one, lastly. So yeah, so that is the case. So all the threads can read. Then there is a barrier, and then there is one single thread writing, and again there is a barrier. And after that barrier, multiple threads can again read, or one thread can perform write. So we can separate this reads and a write by a barrier. In that way, we can target the third necessary condition for the data race. And the fourth condition, which is concurrent execution, uh, can be troubleshooted by using something called as mutual exclusion. So what is mutual exclusion? Let us try to understand here itself. So mutual exclusion is the way in which only one thread will execute the critical section. So again, mutual exclusion is the way of ensuring that only one thread will execute the critical section. And what is this critical section? So critical section is the region of or the piece of the code where the shared variables are getting updated. So let me come back here. So this thing, right, sum equals to sum plus x. This sum was a global variable or the common variable across all the threads. So this variable was getting updated, right? So this thing need to be placed inside a critical section, because there is some shared variable or a common variable which is being updated by the thread here. So such lines should be placed in critical section. And what mutual exclusion says is that uh, only one thread can execute a critical section at one time. So if that is the case, then again we can avoid the data race, because shared variables are updated by only just one thread at a particular moment. So yeah, so these are the four ways in which we can avoid the data race, and these are the 4 necessary conditions for the data race to occur. And this all 4 are needed. Even if any one of them is falsified, then data race won't occur. I hope this is clear. Any doubts related to this slide up till now, or any of the slides up till now? Okay, I'm assuming that there are no doubts. In that case, let us move further. Okay, so let us start with a class one. So we have 2 threads now. thread 1 is executing this piece of code, and thread 2 is executing this piece of code, this one. I want each and every one of you to think that if there is a data race in this code, I'll give you some few seconds. I mean, I'll wait here probably for a minute or few seconds for you people to try out. Okay, think about it and please post your answers in the chat, or either you can unmute yourself and ask.
Sir, is it possible that two different instructions of the thread occur at the same time, like at two different levels?
Meaning, you are trying to say that flag equals to 1 is executing, and then some
Other
uh,
instruction, yeah,
this
not
another
the
instruction
first one.
by.
Sir, here the critical section is the S1 and S2, right, sir?
Yes, critical section is S1, S2. Yeah, so I probably forgot to mention that. So S1 and S2 is a critical section here, and assuming that flag variable is common across T1 and T2. So flag is some common variable or shared variable across T1 and T2, and this S1 and S2 are not affecting the value of flag. So the way the S1 and S2 is written, they are not affecting the value of flag. Considering these facts in mind, is there any data race occurring in this code? If yes, then why? If no, then why?
Sir, no, sir, because when the T1 while loop executes, the flag will need to be 1, and T2 while loop will only execute when flag is 0 or the opposite.
Okay. Okay, probably it might be correct answer, but I think we need to analyze it, taking multiple cases. Probably case when flag is 0 and probably case when flag is 1. I will do, but I'm just waiting for others to try so that we can discuss further.
So in the second code, there is no value set for flag. If the value for flag is set in the second code only, then I guess let's say in the first line before even executing the while statement T2.
Okay, here.
Yeah. In case if we set a value before the while loop, and if that value is 0, then definitely a data race can occur
Okay. Yeah, please go ahead. How it can occur?
because when flag is set to 0 and let's say it goes ahead and gets goes into the S2, and then at the same time then after that T1 actually sets the value to 1 and then goes ahead with the while loop and then reaches S1.
Okay, I think probably you're missing something. You are trying, or probably I'm misunderstanding. So let us try to understand your suggestion. Uh, so flag value was 0. You told that flag value was 0. So T2 will start executing. It will see that uh, not of flag, which is not of 0, is 1. So it will keep on waiting here because while 1, it will keep on looping here. It will not move ahead. And meanwhile, let's say it was looping here. Sorry, thread 1 came. It set the flag value as 1. It went up. Meanwhile, this was looping. Let's say flag was set 1, and that it went to next instruction. It also start looping, right? Thread 1 also
Yeah,
start
I
looping
guess.
because while 1. Here it will start looping, but now let's say flag value is 1, so not of 1 is 0.
Right.
This thread 1 was looping here, but thread 2 moved on because thread not of 1 is 0, so it started executing S2. Meanwhile, please note that thread 1 was looping because flag is 1. S2 is executed. Flag is set to 0. Now since flag is 0, while of 0 is false, so S1 is executed, and yeah, execution is finished. So
Right, right.
no data.
Yeah, I guess I just missed one point where flag can be set to 0 after the while loop. In that case, yeah,
Okay.
just after the while loop.
Okay. Flag can be set just after the while.
Instead of before,
Yeah.
after S2, set it before S2. But
Okay,
that
in
makes
that
sense.
case
If
it
it's
might
a
be,
public
I mean, but here we are setting the before, uh, okay, let me try to understand that also. Uh, let's say flag was 0, we came here, okay, we were waiting here, flag was
the
set to
flag
1,
was, we can keep it 1 for both the cases. Um,
but still there won't be data error, I guess.
yeah, there won't be data errors, right? Understood.
Uh,
It's opposite polling loop. Yeah,
yeah,
that makes
yeah,
sense.
yeah.
That's
So, yeah, so anyways, that was a good discussion. I think there are no other responses. Anyways, let's continue with this. So let us analyze this case by case. In order to understand if there is a data race or not, we need to take multiple or all possible cases and then understand what will happen. So let us say the case one is flag is not, sorry, flag is 0. In that case, let's say either of the interleaving is happening. Let's say flag was set to 1 and then this statement was executed. This flag was set to 1 by T1 and then this statement was executed. In that case, not of 1 will be 0, so this will be moving on. It will execute S2. Meanwhile, this one will be waiting here because flag is 1 and then flag will be set 0. And since flag is 0, T1 will proceed to S1 and that thing will happen, right? So there is no data race because S2 is executed then S1. Okay, fine, no data race because no two critical sections are being executed simultaneously. So please note that there is no data race. So yeah, so S1 and S2 are the codes corresponding to critical section, and since no two critical sections are being executed simultaneously, we are saying that there is no data race. Okay, so please keep that in mind. So that was first case. I mean, for the flag equals to 0. I mean, one another interleaving is also possible. Let's say that initially flag was not set to 1 by T1, but let's say T2 started first and it started executing this while loop. And since flag was 0, not of 0 is 1, so it will keep on looping here. Meanwhile, since it is looping here, it will not move on. Meanwhile, thread 1 came here. It set flag to 1. Now, since the flag is 1, this will not, I mean, this will halt looping here because not of 1 is 0, so it will move on again. S2 will be executed and then flag will be made 0. And again, this while loop, since flag is 0, this while loop, this thread T1 looping at this while loop will move on, then S1 will be executed. Fine. So that is the case for uh, flag equals to 0. When flag equals to 1, again we can see that this holds true. No two critical section can be executed simultaneously. When flag equals to 1, let us say that T1 executed this first, flag equals to 1. In that case, again same thing will happen, right? Because flag was set to 1, again it was resetted to 1 by this T1. So this here T2 won't be looping because not of 1 is 0 and S2 will be executed and flag will be set to 0, and then again this uh, T1 will move out of this loop and will execute S1 and so on. So you can try out multiple combinations of this three statements. Probably there will be many combinations for two cases. One is the case where flag is 0 and another is the case when flag is 1. So you won't be able to see any of the case where S2 and S1 are being executed simultaneously by thread T1 and T2. And if that is the case, we can say that there is no data race in this code. Fine. So I hope that this part is clear. If there are any questions related to this thing, data race thing for this code, then please ask by unmuting yourself. Else we'll move further. There is some question. The definition of data race does not talk about critical section. Thus all two conditions of the definitions are satisfied. Thus all doesn't all two conditions of the definitions are satisfied. Okay. So you're trying to say that. Okay, I didn't probably catch your point properly, but can you try to elaborate this or probably unmute yourself and ask how we are satisfying all four conditions? Okay, I'll waiting for your.
Let Are you able to hear me?
Yes, yes, I'm able to hear you.
Okay, if you go to your definition of data race, right? Maybe I'm misunderstanding. You mentioned if all the four conditions hold, right? So I think we have multiple threads. We are accessing flag, which is a common memory location. We are like writing once to flag, like twice to flag, and we are executing concurrently, right? So I mean, by this definition, doesn't like all four conditions satisfy in T1 and T2? So
Correct, correct. This observation is very crucial. Actually, I was hoping that someone should point this out. So, if you see, uh, we are actually satisfying all these four conditions. If you see, if you are able to get it correctly, we are satisfying all these conditions here. In fact, if you see here, flag is being written by value 1, and at the same time, thread 2 is being thread 2 is reading that value. So there is writing happening into the common memory location, writing happening into common memory location by multiple threads, and there is also concurrent execution. But still, I'm saying that it's not a data race. Why? So let us understand this. In some sense, this is a data race, but let us try to understand it more in more detail. So if you see at assembly level, uh, this instruction setting of flag to 1 is a memory write operation. So let me go here. So this memory write operation will just, I mean, it will happen atomically. So if there is some operation like this, addition or something, which was here, if you see this addition operation, it is split into 3 operation, right? Like this. But if there is some operation like this, where we are doing writing, then it's just one assembly operation. And that single operation is done atomically, even if there are multiple threads. So it won't happen that, I mean, at the same time, thread 1 is writing into flag, as well as at the same moment when it is getting written, this thread 2 will be reading that value. So yeah, interleaving is possible. Flag 1 is written by the value 1, and then flag 2 will be reading, or flag 2 will be read first by thread 2, and then writing will happen. So interleaving is possible, but simultaneous reading while writing is also happening will not occur because of the way the assembly instruction executes. If there are multiple, if one statement is being splitted into multiple assembly level instructions, then any of the interleaving can happen, and we can get such incorrect outputs that we saw here, right? But here there won't be a data race. I hope you are getting it. In some sense, you can say yes, these four conditions are getting are being holded here. But from correctness perspective, there won't be any issues, and hence I'm saying that there is no data race. I hope you are getting it. If there are any further suggestions, if there are any further questions, Jayaraman, then you can unmute yourself and ask. Okay, there is some, sir, but both while loops have a chance to execute together now. Gokul, can you unmute yourself and tell me how both the loops can execute simultaneously? Well, you are, your observation is correct, but I want you to elaborate on it.
Sir, based on the timing, sir, let's assume that flag is 0 initially, and now in thread 2, the control is entering into through the while loop and into first statement of while loop, right?
Okay.
At the same time, in the thread 1, the control is not yet gone to flag equal to 1. So the while loop is entered in T2, and then in T1 the flag is set as 1, and then control enters there. And by the time T1 while loop is over, before that T2 while loop will reach flag equal to 0, and then before flag is again reset to 1, thread 2 will go back into the while loop. So it will keep missing each other, and both of them will happen together.
I missed your part. Like initially thread was 0, flag was 0. If flag was 0 initially, T2 will wait here. I understood till that part. Now what next are you trying to do? You are doing something with this part, right? What you are doing? Can you please?
Sorry, sir. Let's.
Yeah, but in that case,
Sir,
there won't be again. Yeah, yeah. Please go ahead. Yeah.
Initially flag 0 means T2 will not wait now. So it will go into while flag not 0 will become 1 and it will enter right now, sir.
No, if flag is okay, I think you are misunderstanding. If flag is 0, then not of flag is 1, and while 1 is always true. I mean, 1 is like true.
It
So
will
right,
enter now, sir.
no, it will not enter. It will keep on looping here. While not of flag means, and if flag is 0, is similar to while 1. And if that is the case, it will keep on looping here. I hope you are getting it. And if it keeps on looping here, it will not enter. I hope you are getting it.
Got it, sir.
Okay. Yeah, anyways, let's move on. Okay, so next question that I want to ask you people is what this code ensures. Does this code ensures anything? Any typical thing in the way the critical sections are executed or anything else? Does this code ensure anything? First thing that we can ensure is one thing that we can ensure is for sure, right? That it ensures mutual exclusion because as we understood as we know the definition of mutual exclusion, if only one thread enters into the critical section at particular time, then mutual exclusion is ensured. And here exactly that thing is happening. So mutual exclusion is ensured. But any particular thing related to the way the critical section is executed? Any comment about that part that you people want to make?
Sir, like we can say that we are setting a flag and allowing only one of the threads to enter the critical section.
That is what is mutual exclusion. I told that we are sure about one thing, that mutual exclusion is guaranteed based on this mechanism that we have implemented using flag. But there is something else apart from that that I want you people to point out. This code ensures something else. Something more apart from the mutual exclusion. Meanwhile, I'll take questions or whatever. Okay, that part, yes, that makes sense. Okay, that's fine. Atomic means only one write at a time, just to clarify. Okay, so atomic means something else. So I'll explain you with the example. So atomic is something like this. You are testing and setting the value of that particular variable atomically. So what is testing and setting? Let us understand this. So if you see here, you are testing the value, right? You are reading the value. In some sense, you can say that you are testing the value, and here you are setting the value by putting the value of the content of register into sum. So you are testing and setting the value. You want to do this entire thing atomically, and that is actually what is that is what is done by atomic instruction atomically. So no other thread can execute while these three assembly level statements are being executed. That is what atomics ensure. Testing and setting is done atomically. That is what atomics ensure. S2 is outside the loop. Yeah, S2 is outside the loop. I hope you are getting it. So this semicolon marks the end of this while loop. I hope you are getting this. S2 is outside the loop.
Yes, sir, got it.
S1 is also outside. Okay, anyway, since we are running out of time, let us continue with this. So what this code ensures, it ensures mutual exclusion, that is for sure. What it ensures more is that if you see in each of the cases that we tried to analyze, right, when flag equals to 0 and then different execution patterns, and flag equals to 1 and then we tried executing in different fashion, we saw that uh, first always S2 is executed and then S1. So this code ensures two things. One is mutual exclusion. It's mutual exclusion, and second thing is S1, S2 will be executed followed by S1. So these two things are ensured by this code. So I hope you are getting it. If you are still confused about it, you can try multiple ways in which this code can execute with different values of flag. 0 and 1 are the different values of flag. You can take both the cases, and you can try different interleavings of this code and interleavings of this statements, not code, across thread 1 and thread 2 and try to see which executes first and which executes second. So you will see that S2 will always execute first and then only S1 can execute. But there is still one more catch. Okay, we'll come to this. Can we generalize this mutual exclusion for AND threads? But there is still one more catch to it. And what is that catch? It's here. So if initially flag is set to 0, then S2 execute before S1. That we saw, right? When flag is 0, we saw the cases where flag S2 was executing before S1. But if initially flag is set to 1, then S2 executes and then S1 executes. So that is consistent with the flag equals to 0. But there is something else that might happen. Or the thread 1 may hung, or I mean thread 1 may fall into infinite loop. So can anyone point out the execution pattern that that is possible such that thread 1 hangs? Uh, yeah, please think about it. The case when
Thread to execute. Oh, sorry.
yeah, go ahead.
Thread to executes the whole thing till flag equal to 0, and flag equal to 1 had already been set in the thread 1. It had been executed before, and now since flag is 0, the while loop is stuck in the
Yes,
thread
yes.
1.
So, yeah, so uh, what he's trying to suggest is that let's say that flag was initially 1, so not of 1 is 0. So thread 2 will move further, then S2 will be executed, and just before that, let's say thread 1 has also, I mean, when S2 was being executed, thread 1 set flag to 1. Now, okay, sorry, no, sorry, I just misunderstood it. S2 was being executed, flag was 1. Now, let's say that flag was set to 0, and then T2 finished its execution. So T2 finished. Now, thread 1 came, it started executing, it made flag to 1. Now, since flag is 1, while of 1 is true, and it will keep on infinitely looping here. So thread 1 might hang because thread 2 has already finished its execution of this statement, and flag will now never become 0 after becoming 1 here by the, I mean setting 1 here by the thread, and here thread 1 will keep on looping infinitely. So I hope you are getting it. Two cases here. Uh, Either S2 is executed before S1, that is first case. S2 executes before S1, and the second case is T2 executes completely. I mean S2 executes completely and thread 1 hangs. I hope you are getting. Sorry, is there any question? Hello. Okay, I am assuming that there are no questions. Okay. Please unmute yourself unless you have any questions. I can hear some noise from someone's. I think. Okay, anyways, if you have any questions, then you can unmute yourself and ask. But unless, I mean, otherwise, please mute yourself so that our discussion can move smoothly. If T2 is called multiple times, it may lock out T1 completely too. Yes, that is correct, Gokul. I mean, T2 can execute multiple times and it can set flag to 0. And let's say T1 comes after it for execution. In that case, it won't be able to execute further since flag is set to 1 before it starts executing its critical section. Flag is always set to 1 each time, right, by thread 1. Yeah, so that is correct. So let's move on from here. A small classwork for you again. So,
Sir,
yeah.
sir, I had a doubt in the previous slide. Could you please go there? Yes, sir. So, like we were saying that flag is initially 0 and the while loop is running. So, it will come out of that while loop only if flag is set to 1, right?
Okay. Here.
So, yeah, yes,
Right.
sir. So, in,
Okay. So, yeah,
so
that is
in,
fine.
and then the flag will be set to 0 and then it will never enter the while loop, right? The T1 while loop.
Okay. I missed. I mean, what is your doubt? I missed that part.
So like why D1 may hang? Like I didn't get the point.
Okay, let us understand that this thing. So let us say that flag value was 1. It was not 0 first of all. Flag value was 1, right? So if flag value was 1, not of flag is 0, right? Not of 1 is 0. So T2 will not stop here. It will move on right here. It will
Yes, sir.
execute S2. It will execute S2. It will set flag to 0, right? And then it finished its execution. Is it okay till now?
Yeah, yes, I got it.
Okay, now thread 1 came, it started executing, it set flag to 1, and then it came here. Now since flag of 1 is true, I mean flag of 1, which is flag is 1, so while of 1 is true, it will keep on looping here. And now there is no thread to set the flag value to 0. So it will keep on looping here because there is no one to make that flag value to 0, and it will
Yeah, yes,
never
sir.
move on.
Yeah, yes, I got it.
Okay, so I hope that you're getting it. Any further questions apart from that? It's important that we understand these things. Otherwise, later I mean, as we go deeper with atomics and all those things, it will create more confusions. Okay, anyways, feel free to ask questions. So let us try this classwork. We are given roll number and marks of 80 students in the GPU programming course and or CUDA programming course, and we need to assign the grades for those students. So grading system is like this. If your marks are 90 or higher, then you get some S grade. 80 to 90 you get A. 70 to 80 you get B, and so on. D, C, D, and E is for 40 to 50, and U for less than 40. And you need to read the inputs from the input array. So input array is given, which consists of values, and that values denotes the marks of that particular student. So let's say student has some roll number, and that roll number is itself the index of that array. So student with roll number 0 has some marks which is placed in ARR of 0. Student with roll number 1 has some marks which are placed in ARR of 1, and so on. We read those marks from input array, and we want to output the histogram like this. So you want to essentially tell that how many students have U grade, how many students have E grade, how many students have D, C, or B, or A grade. So we want to essentially count the number of students based on the grade. So for grade A, how many students are there, and so on. So yeah, so that is some sort of an histogram computation. So how can we do that? Count the number of students with a particular grade. And that is what we are interested here. This takes some time to think about how will we write the code corresponding to it, and will there be a data race involved here or not. Please take some time. Meanwhile, I'll look into the chat if there are any questions. Okay, I guess there are no questions so far. Okay, please think about this and post your answers in the chat, or either you can unmute yourself and ask. Yes, I think Varun's suggestion is correct. Writing in the output array, updating the value as data arrays. Yeah, so can you unmute yourself and explain why there is a data arrays, like the way you are computing it and the way it is
Yeah.
causing data arrays? Yeah.
So essentially, we compute for S, there can be multiple students.
Hmm.
So let's say the array index 0 and array index 1 of 2 have uh, values greater than 90, then both of them correspond to the updation in the same output array, which will be 0. So you'll be updating the value to increase the value by 1 in
Correct.
both of the cases. Now, yeah, so in that case, if only they can occur parallelly, and probably only one update can happen on those.
Yes, correct, correct. So that is one scenario where the data race can happen. Can you think about the way in which we can avoid that data race? So that is the next question. Your answer is correct that if there are multiple threads, I mean there are multiple students which have marks above 90, or let's say about above 80, in between 90 and 80, having A grade, then multiple threads will try to write into that variable which we use for keeping track of that particular grade, and hence there can be a data race for incrementing that student count for that particular grade. So there can be inconsistency there, but how can we avoid that thing is I want you people to think. And moving on to Rishikesh's suggestion, can we declare a count array entries corresponding to number of students in each grade? Since thread access same element in the array, data is will occur. Yes, I think this is also very similar to Varun's suggestion. Number of students in each grade. Yeah, similar to I think Varun's suggestion. Where output array is first by difference, but each cell in the array is a different memory location. Yeah, each cell in the memory, each cell in the array is a different memory location, but there are multiple threads which are writing to one particular memory location, right? So let's say for S grade, I mean, there is only one entry for the S grade, but there can be multiple threads or multiple students who are having S grade, and for updating that count of that student inside that same memory location which is used for keeping track of that S grade, uh, we'll be doing, I mean, multiple threads will be writing in that same memory location. So that is where the data race comes. Even though we have seven, because from S to U, there are 7 grades, right? 7 possible grades, 7 different memory locations are there. But multiple threads can write into one particular memory location out of that 7. So I hope you are getting that, Gokul. Okay, let me go by order. We could do this where each thread has its own count value, and we can add them to add them two at a time. I didn't got your point, sorry, but we could do this where each thread has its own count value, and we can add them two at a time. Yeah, probably I'm getting this. Probably we'll come to this thing. Probably we'll see how we can keep one count for each thread. So that is another way we can do it. Let's come to this itself. So what we can do is,
Sir, one thing
yeah, please go ahead.
sir, one thing we can do, that if there are 10 threads, so a array of 10 elements will be used in the shared memory. So likewise, parallelly, one array of flags of 10 elements can be, or 10 flags can be used. Array of 10 flags corresponding to each element for the count of a particular grade.
Okay. And how can we? I mean, how will we avoid data race with that 10 grades or 10 elements corresponding to each grade?
So whenever a thread will try to write some data element, some array element in a particular grade, so the corresponding flag will be checked.
Okay, you are trying to say something like this. Something like this you are trying to say. You can we can implement such flag kind of mechanism.
Yes, instead of
For each.
2, there will be the number of grades. So if the number of grades are, number of categories are 10, or number of grades are 10, so array of 10 flags will be used.
Okay, fine. 10 flags, array of 10 flags. Instead of just one flag, 10 flags. Okay. Then you need to write the code in such a way that their critical sections won't be executed at same time. So you need to write the code corresponding to it, which will be slightly complicated, I would say, but yeah, you can do that. That's one of the way it can be done. Okay, that's one of the I'll say correct suggestion. Uh, we can implement mutual exclusion by setting flags. Yeah, that is, I mean, that is what this example was suggesting. We are implementing here mutual exclusion by using some flags. So yeah, that is correct, Rishikesh. But I was here with Gokul's suggestion. We could do this where each thread has its own count value, and we add them two at a time. I didn't catch up this last part, but yeah, let us come to this thing. Each thread has its own count value. So what can we do here is one of the naive way or the very intuitive way of doing this is as suggested by many of you. What we can do is what we can do is like each thread based on, I mean, it will be assigned some element based on its ID in that array, and it will increment the particular grade. I mean, here the grade will be an array of 7 elements, because from S to U there are 7 grades. So it will increment that particular location in that array of size 7 based on that element in that array, ERR, right? So that is one of the way, but that will have data race, as we saw. But in order to avoid this data race, what we can do is we can just keep this array of size 7 and just declare, I mean, launch a kernel with just 7 threads, one thread for each of the grade. So I hope you are getting it. We are launching kernel with 7 threads, one thread for each grade. And what each thread does is it goes through all the elements of the array, and if it finds the element inside that array to be falling in that grade category, it increments the it increments the value of that array element by 1 if it finds that student. So I hope you are getting it. Each thread goes through the entire array based on its criteria for that grade on which it is working. It will increment the value accordingly. So one way is to go by student, one thread for each student. Second way is to go by grades, one thread for each grade. In first approach, one thread for each student, there will be data race and we'll need synchronization or we'll need to use atomics. But here in the second case, one thread for each grade, opposing to that previous case where we have one thread for each student. Here we have one thread for each grade, and here there will be no data race. But if you see here, we need to do more work, right? Each thread has to go through the entire array. So yeah, so I mean, if you want to get some kind of balance, you can combine both this approach and try. I mean, first approach there is data race. To avoid that, you need to add atomics. So there is also overhead there, and here also there is overhead. In second approach, you need to go through the entire array. So you can combine both this approach and try to see what are the benefits and how can you, and what percent you can combine both of this approach, and you can try seeing what are the advantages and limitations. So I hope that is clear. Any questions up till this point for this slide or any of the previous slides?
Yes, one quick question. So if the
Yeah.
number of students is way greater than the number of categories, so in
Hmm.
that case, it will still be expensive to go over that big loop every time in each thread,
Actually, yeah,
right?
that's a very valid question. If let's say number of students are much greater than number of grades, because particularly grades are just 10 and now students can be in thousands. So in that case, it won't be good to do that. But what we can do is we can try combining both the approaches based on the number of grades and number of students. So I hope you're getting it. Or did I miss your question?
Yeah, that was my question. Thanks.
Oh, I I was here. I think I also took this. Can we implement mutual exclusion by setting flags? Yeah, so we already saw the example for it, right? We implemented mutual exclusion by implementing flags, using flags, sorry, by setting flags. Or we could sync thread and have one thread to do counting. Yeah, I'm not able to properly get your suggestion, Gokul. Probably you can unmute yourself and ask what I mean. Unmute yourself and explain what are you trying to say with this. And sync thread will be only for the threads of the thread block. So let's say students are very large in number, let's say even beyond 1024, then you need to launch the kernel with more than 1024 threads, and I mean with multiple blocks essentially. So that sync thread won't help in synchronization. So I hope you are getting that point. There will be some issues, but you can try writing in the way you are describing. I hope that is clear. Okay, anyways, if you have any questions further, then you can unmute yourself and ask. Okay, so moving on, let us see this last slide. So let us say that we are interested in computing the shortest path from, let's say, some city, Indian city, let's say Nagpur, which is the center of the India, to all other cities. So we are given the graph as input, graph of India as input. And we want to compute the shortest path from the center of India to all other cities. So for that, what are the different algorithms that you can use? We can use multiple, I mean, there are multiple algorithms available for finding the shortest path, right? So you can use Dijkstra's algorithm or Bellman-Ford algorithm. So we'll be using Bellman-Ford algorithm here, for example. So let us try to understand it. We want to compute shortest path from India's center to all other cities of the India. So okay, so for doing that, let us say that you are also given with the GPU graph library, which computes, I mean, which has some inbuilt functions like reading the graph and let's say finding, I mean, going through all the neighbors of a particular vertex, and also, I mean, you have functions for finding the distance, I mean, getting the distance between the particular vertex and its neighbor. So all these routines are given to you, and you are interested in finding the shortest distance. And the way it is done is like this: each thread operates on a node based on its ID. Let's say ID of thread is 1, then it operates on node number 1, and it settles the distance of its neighbor. So what it does is, it based on its distance, it will compute the distance of its neighbors, and if the computed distance is less than the original distance of its neighbor, then it will update its neighbor's distance, the way we do in Bellman-Ford algorithm, right? So in Bellman-Ford algorithm, we say that we relax all of the neighbors of a particular vertex, if you remember. So yeah, that is what we want to do here. And for doing that, let us say that we are writing this triple SP subroutine, D triple SP, which is device triple SP, which is GPU code for the triple SP. And what it does is, it reads this graph as input, which is some, let's say, class or some structure, and it's reading this graph as input, and the array of distance. So this distance is an array of size v, which is number of vertices, and it stores, I mean, it stores the shortest distance from source to all other vertex. So initially it will be initialized as so it will be initialized like this. It will the distance for the source vertex will be 0, and all other vertices will be infinity inside this distance array. And as this computation proceeds, they will get shortest distance from the source vertex and source vertex to all other vertices. Yeah, so this is the code corresponding to it, but let us see this figure first. So here the A is source, and let's say we want to compute shortest path to all other vertices, B, C, D, E, F, G, all the other vertices. And yeah, we have some edges, I mean, edges to reach those vertices. And for computing the shortest path, we use this GPU kernel, which is named as D triple SP. And inside that kernel, we compute ID using our normal that equation, right? Thread ID x dot x plus block ID x dot x into block dim dot x, right? That equation we use to get the unique ID. Once we get the unique ID, each thread based on its ID will work on that particular vertex. So let's say if ID is 0, then it will work on vertex 0. If the thread's ID is 1, it will work on vertex 1, and so on. So what each thread will do, it will go through all its neighbors based on its ID. So if thread with thread as id 0, it will pick up the vertex 0, it will go through all its neighbors, and what it will do is it will first of all check its distance. It will add the uh, distance from it to its neighbor into that distance, and it will call that thing as alternate distance. So let us say you want to compute the shortest path from let's say from yeah, okay, let's say we want to compute the shortest path to C. Then what this A will do, initially C will have distance as infinity, right? Because this is the way we have initialized it. So A will have distance 0 since it is source. Every other vertex will have distance infinity. And so what A will do, it will go through all its neighbors. So let's say it went through C. Its distance was 0. So dist of 0 is 0 plus weight of id comma n means 0 comma 0 comma c or a comma c, you can say, which is 3. So 0 plus 3 is 3. So alternate distance to c is 3, and 3 is less than distance of n, right? Because distance of n, which is distance of c, was initially infinity, sorry. So infinity is less than infinity is greater than alternate distance, which is 3. So 3 is less than infinity. So it will update that distance of n, which is distance of c, to 3. So I hope you are getting it the way we are computing it. Any questions up till this point, like for this computation part, this cardinal part? Quickly. If there are no question, I'll ask you one question here, and then we'll probably conclude for today. Okay, I can see there are no questions. Okay, in that case, I'll ask you one question. What is the problem with this code? There are two problems, or let me simplify it since we have less time. There are two places where there are data race occurring. There is data race occurring. There are two places where the data race is occurring. Can you quickly point out the two places where the data race will occur? I hope that the question is clear. There are two places where the data races are, at least two places where the data race is occurring. But I want you people to point out two places where the data race is occurring.
Sir, inside that if statement where we are assigning distance of n, there we can have a data race, like two threads might be assigning.
Okay. Yeah, that is correct. But I want a more elaborate argument for this, right? Yeah, that you are correct that two thread might at same time try to assign that. But can you explain it with example here? Like, or probably I'll
Like,
explain it.
for
Okay, okay.
example, if we take C, then in that case it is neighbor of A and D, both of them. So in like if both the threads are running parallelly, then it might appear in that if statement at the same time. So we can write the distance of C.
Okay, so your argument is correct, but there is one small thing that you are ignoring here. I'll add that point here. So there is data race occurring, but there is one more crucial issue here. The data race is there, but it is affecting the correctness, if you see. And why it is affecting the correctness, let us try to understand. There is reading as well as writing happening simultaneously. So reading of distance is happening here, here at this inside this if. Distance is being read and also being written. So let us try to understand what is happening. So let us say A was trying to update the shortest distance to C, and D was also trying to update shortest distance to C. And we know that shortest distance to D was 4, right, because of this A. And let's say D to C edge was having distance of 2, or let's say 3. So 4 plus 3 is 7, right? So, and initially C's distance was infinity, right, because no one has approached till C right now. So what happened was D read the value of distance of n, and n is C here. Please note that neighbor of A and D is C. So n is C here. So distance of n is infinity. No one has yet updated. What both A and C read, the value of n was infinity, right? Because distance of n was infinity. Both A and C read the value of distance of n as infinity. Now both of them the altered distance is less than infinity, right? Because for A it's 3 is less than infinity. For D it's 4 plus 2, 4 plus 3, which is 7. 7 is also less than infinity. Now since both has the value of 3 less than value of dist10 which is infinity, uh, since both of them has alt dist which is 3 and 7 respectively less than infinity, both of them will enter in this this if condition, and based on whosoever updates the value of dist of n last, you might see the final value of distance of c, which can be either 3 or 7. If d update its distance last, then the value of distance of c will be 7. If a updates its distance value last, its distance value will be 3. But what is the correct answer? It's 3, right? Shortest distance to c is 3 by route of a, I mean through a. But it might happen that here t might be the last one to execute, last one to finish this statement because of the data race, and due to that the shortest distance to c might be 7. So that is one problem. And second issue that might happen is that this reading and this writing might happen simultaneously, this reading and this writing. So let's say this thread which was working on vertex A was executing. It updated the value of distance, which is distance of B, which was here, which was its neighbor. It updated the distance of B after the no before the B read the value. So B will read this value infinity, but actually after updation the alt distance was 7, right? Because A will update it. So this B is updated to 7, but A, the thread which is working on B saw its garbage value, infinity actually, not garbage value, infinity was seen by B. So B saw infinity here while reading, but A updated later and updated it to 7. So this is also the second case where the data race can happen. So I hope it is clear. If there are any questions here for these two cases, then you can ask. We are already out of time. So
Second case, its correctness is not affected though, right?
yeah,
Because
that is one important point that I missed specifying. So correctness is only affected for the first case, for the case where the data race was between these two things, this reading and this writing. But for the second case, when there is data race for this reading and this writing, correctness is not a concern, because let's say B's value was updated later after the B read the value. But okay, let's say that it read the value as infinity. The thread working on B read the value infinity. But let's say this triple SP was getting executed multiple times. Then in second run, it will see the correct value, which is 7. So in that case, correctness is not the issue. But the more serious issue is with case 1, which actually can cause the correctness issue. So yeah, please note that point. Yeah, so case 1 is causing correctness issue. Case 2 is just is causing data race but not correctness issue. So I hope it is clear. If there are any questions, then you can unmute yourself and ask.
Sir, can you repeat the case 2 once more, sir?
Okay, so case 2 is let us say that we have this A and B vertex and threads working on this vertex A and vertex B. So what will happen? Let us understand. So thread which is working on this vertex A is trying to update this distance to 7, right? Distance of B to 7. Meanwhile, thread working on this vertex B is also reading its value right here, because it wants to update the distance of its neighbor, so it must be reading its value. So let us say that reading of B, which has its initial value is infinity, is done before this writing is done by the vertex A. So vertex A is trying to write 7. Vertex A is trying to write the distance as 7 into this distance of 7 into this B's final distance, right? But what happened is 7 is written after the B has read the value from its distance array, which is infinity. So B read infinity, and based on that it is trying to update the value of its neighbor, but since it is infinity, it won't update anything. And after that A wrote the value 7 into B's distance. So that is fine. I mean, that has data race. I mean, reading and writing are being done simultaneously, but that won't affect the correctness because B's distance is updated, right? It will be visible to the thread working on the vertex B in the next iteration when this triple SP kernel is invoked. I hope that is clear. If still there is any confusion, then you can ask.
Yes.
Okay. Any further questions? I'll be there here for a few minutes. Yeah, please ask if you have any questions.